All right, let's dive right into this explainer. Today, we are going to completely demystify exactly what happens under the hood of modern AI systems. A lot of folks think machine learning just magically appeared the day they asked a chatbot to finish their homework, but the story is actually way deeper than that. So, we're going to trace the entire journey, literally from raw, basic data all the way up to the massive models like ChatGPT. To get us there without getting lost, we'll follow a pretty clear roadmap. 1. From rules to learning. 2. The basic ML ingredients. 3. How models actually learn. 4. The neural network upgrade. And finally, 5. Inside modern AI systems. Section 1. From rules to learning. Now, AI absolutely isn't some overnight phenomenon. It's a decades-long journey. Way back in 1950, Alan Turing was already asking if machines could imitate human intelligence. Jump to 1997, and IBM's Deep Blue actually beats the world chess champion Garry Kasparov. But here's the thing. Deep Blue was a highly specialized, rule-based system. It couldn't translate a language or drive a car. The real explosion, that hit in 2012, when a neural network named AlexNet just utterly dominated an image recognition competition using GPUs. That kicked off the modern deep learning boom. And then 2017 brought the transformer architecture, which is literally the foundation for the massive language models we all use today. The real paradigm shift here is fascinating. In traditional programming, humans write explicit rules. If a user is over 18, allow access. It's simple, clean logic. But imagine trying to write rigid rules to catch spam emails. Spammers change their wording constantly, right? If you manually code every single rule, you'll just never catch up. Machine learning completely flips the script. Instead of telling the computer the rules, we give it the data and the correct answers. And the system actually learns the underlying rules and patterns entirely on its own. Moving on to Section 2, the basic ML ingredients. So what do our raw materials actually look like? Let's take a classic beginner problem using a housing data set. Every row in our data is a single example, like a specific house that's sold in the past. The columns describing the house, like the square footage or the number of bedrooms, we call those features. Those are our inputs. The value we actually want the model to predict, which is the final sale price, is called the label. When we train a model on data that already has the correct answers attached, we call this supervised learning. We're essentially saying, hey, here is what the house looks like, and here is exactly what it's sold for. Now, learn the pattern. If you've ever wondered how websites estimate your home's value, this is exactly where it starts. Okay, so how does the model actually use those features? Well, under the hood, it uses an equation where it tunes internal values called parameters. Think of these like little mathematical knobs. A weight is a parameter that controls how much a specific feature matters. So if the weight for square footage is tuned really high, the model has decided that the size of the house heavily impacts the price. A bias is another parameter that just acts as a baseline offset. When a model learns, all it's really doing is turning these knobs until it gets better and better at predicting the answers. Which brings us to Section 3, how models actually learn. If a model makes a guess, how does it know if it's right or wrong? Imagine our model predicts a house is going to sell for $700,000, but the actual label says $800,000. As humans, we immediately know it's off by $100,000. The model uses something called a loss function to quantify this mistake. Think of the loss function as the ultimate unforgiving report card for the AI. It gives the model a super precise mathematical feedback signal. We actually often square the error so that massive mistakes are punished much more severely than tiny ones. The entire goal of training is incredibly simple. Make that loss as small as mathematically possible. Once we know our loss, we use a process called gradient descent to fix the parameters. Imagine a ball sitting on a hill, where the height of the hill represents our loss, our error. We obviously want that ball to roll all the way down to the lowest possible point. Gradient descent calculates the slope of the hill and tells the model exactly which direction to adjust its weights to move downwards. A specific setting called the learning rate decides exactly how big of a step we take. If the step is too small, learning takes absolutely forever, but if it's too big, we might just overshoot the bottom entirely. When we put all of this together, we get the complete training loop. The model takes a batch of data, makes its predictions, and calculates the loss to see just how embarrassingly wrong it was. Then, gradient descent kicks in, updating all those parameter knobs. It moves to the next batch and repeats the process. Once it has seen the entire dataset, it's completed one epoch. The model isn't magically memorizing the answers. It is quite literally just repeating this mathematical cycle over and over again to slowly tune its parameters for better predictions. But there is a massive trap here called overfitting. If a model just memorizes the training data, it's gonna fail spectacularly in the real world. To prevent this, we quarantine our data into 3 very specific splits. We train on roughly 70% of it. Then we use 15%, the validation set, to check our work and tune the model during development. Finally, the test set is a pure, untouched 15% that we hold back until the very end. This ensures the model can actually generalize its knowledge to brand new, totally unseen examples. Before we move on, it's definitely worth noting that supervised learning generally tackles 2 distinct types of problems. Depending on the label we want to predict, we either use regression to pinpoint a continuous number, or we use classification to sort things into buckets or categories. To put it simply, when your weather app predicts it's going to be exactly 72 degrees, that's regression. When your phone categorizes a photo in your camera roll as a dog, that's classification. All right, section 4, the neural network upgrade. So a single equation with some weights is great for spreadsheets, but it's pretty terrible for recognizing images or text. This is exactly where neural networks come in. A neural network takes our simple parameter math and links it into simulated neurons across multiple layers. The input layer takes in the raw data, like pixels. Then come the hidden layers. This is where the magic really happens. They process this data, automatically engineering their own features, like finding the perfect edges, shadows, and curves in a photo, all without us ever telling it how. The output layer gives the final prediction. And crucially, they use activation functions, which are just mathematical rules that allow the network to learn incredibly complex patterns, way beyond just straight lines. But how on earth do you train a network with multiple layers and thousands of interacting weights? You use an algorithm called backpropagation. When the network makes a prediction and the loss function calculates the error, backprop steps in. It traces the error backwards through the complex web of neurons, figuring out exactly who is to blame for the mistake. It calculates how much every single weight and bias contributed, giving gradient descent the exact map it needs to update the entire system. To really put deep learning into perspective, you have to think about scale. Our simple house pricing model used about 80 parameters. A modern neural network like GPT-3, it uses 175 billion parameters. Let that sink in. If every parameter was a second in time, it would equal roughly 5,500 years of tuning. It is the exact same underlying concept: inputs, weights, biases, layers, and math, but scaled up to an absolutely mind-boggling degree, fueled by massive datasets and crazy powerful computer chips. Let's bring it all together in section 5, inside modern AI systems. Modern models like ChatGPT aren't just trained in one shot. First comes pre-training. We feed the model massive amounts of internet text and force it to simply predict the next word or token. It basically acts as the ultimate autocomplete, learning grammar, facts, and reasoning along the way. But we don't just want autocomplete, right? We want a helpful assistant. So next is instruction fine-tuning, where we show it specific examples of how to answer commands. Finally, we use RLFH, reinforcement learning from human feedback. This is where humans actually rate its answers, shaping the model to be helpful, clear, and safe, rather than just mathematically accurate. But how do we know if our training actually worked? We have to grade them. For a regression model predicting house prices, we look at mean absolute error. Are we off by $50,000 on average? For classification, we look at accuracy, precision, and recall to make sure we're actually catching the spam. But for language models, there isn't always one perfect answer to a prompt, so we have to rely on a really complex mix of standardized benchmarks, human preference ratings, and real-world testing. The landscape today is expanding far beyond a simple text chat box, and it is genuinely incredible to watch. Back in 2017, the Transformer architecture introduced attention, which allowed models to understand the deep context between multiple words in a sentence all at once. We're also seeing the explosive rise of multimodal AI, where systems process text, images, and audio simultaneously, letting you generate a stunning picture of an astronaut riding a horse literally just by typing a quick sentence. Finally, we have agents. By giving models access to tools, they can now search the live web, write and run their own Python code, and even manipulate your spreadsheets, taking real actions in the real world. Which brings us to a fascinating close. Everything we've covered today, from a simple spreadsheet predicting house prices to an agent writing Python code, is built on the exact same foundation. It's a system learning from data, guided by a loss function, and adjusting its parameters through gradient descent. Even when modern AI feels like pure magic, it's really just this exact same math loop operating at an incredible, unprecedented scale. So, knowing that it's all just an optimization of a mathematical loss function, how does that change the way you view its intelligence? Thanks for joining me on this explainer. I really hope it gave you a brilliant look under the hood.